Hello everyone and welcome to the third video of the second lecture of the course on metric spaces. In the last two videos we defined the length of a curve in a metric space and we checked that with this definition we can compute the length of a segment connecting 2 points in two different metrics. One, which is the standard one we use on the plane, that says that the distance between P and Q is given by the square root of xp minus xq squared plus yp minus q squared. And the other one, which says that the distance between P and Q is given by the maximum of the absolute value of xp minus xq and the absolute value of yp minus yq. In both cases, we saw that the length of the segment connecting P and Q is exactly equal to the distance between the points P and Q. What we will do in this video is to compute the length of the circle using the definition for the length of a curve. So let's say we fix a circle of radius 1 and we place it in the plane. So the point here is 1, 0, as this is the x-axis and this is y-axis. And this is a circle of radius 1. We know that the circumference of this circle is given by 2 pi. What we want to do now is to prove that the length of the curve, which is exactly given by the circle, is exactly equal to 2 pi when we compute it using the definition we gave for the length of a curve. We will do it for the distance we used since the beginning, which is the one given by the square root of xp minus xq squared plus yp minus yq squared. In order to make this computation, we will consider an angular sector of the circle of width alpha. Recall that given such an angular sector, if we call P and Q the points on the circle of intersection between the two sides of the angular sector with the circle itself, then the length of the segment connecting P and Q, that I will denote in this way, is equal to the sine of alpha divided by 2 times 2. And this is also equal to the distance between P and Q, as we know that the length of the segment connecting 2 points is equal to the distance between the 2 points for the metric given here. Now, to compute the length of a curve with our definition, what we have to do is we have to choose a lot of points on the circle, as many points as we want, and sum the distance between all these points, and then we have to increase the number of points as much as we can. So let's say we draw again the circle we had before, but we make it a little bit bigger. Then we have to take a lot of points on this circle, and let me assume that I fixed a number n positive. So for example, it could be 1, 2, 3, and so on and so forth. And I'm taking angular sectors whose angle is exactly given by 2 pi divided by n. Then we know that if we call these points P1, P2, P3, P4, and so on, the distance between Pi plus 1 and Pi is always given by 2 times the sine of 2 pi divided by 2n. And this is because as the angular sectors have all the same angle, then the length of the segment connecting each of two near points is always given by the formula we had before. So this can be rewritten as 2 times the sine of pi over n. Now, we took n points on the circle, so it means that if we sum the distance between P1 and P2 plus the distance between P2 and P3 and so on to the distance between Pn minus 1 and Pn, this is just n times the number we had before, which means 2 times the sine of pi over n. Now I will place this n here at the denominator, and so I can rewrite this number as 2 pi times the sine of pi divided by n divided pi divided by n. The way we compute length of curves with our formula is that we increase the number of points we take on the curve as much as we can, which means that in this case we have to take n very big. How can we do this? Well, we just take more points on the circle, but as we cannot just take more and more points and compute the numbers every time with our calculator, we need to try to compute the number to which this sum converges, in some sense, which number it approximates, using mathematics. And what I want to show you now is that if n is very big, then the sine of pi divided by n divided pi divided by n is near to 1. And this will tell us that this sum here, as n increases, reaches 2 pi, which is exactly what we want, because we know that if the circle has radius 1, then the circumference has length 2 pi. Now, when n is very, very big, pi divided by n is very, very small. It approximates, it approaches 0. Therefore, this last statement is equivalent to saying that sine of alpha divided by alpha is near to 1 if alpha is near to 0 and positive, because all the numbers we had before are positive numbers. I will show you that this is indeed true using geometry once more. So let me draw another circle of radius 1. Here we go. This point is 1, 0. Then we take a point P on the circle, and if we draw the radius connecting the origin to P, and then we go on a little bit, drawing the line on which the radius lies, we know that the x-coordinate of P is given by the cosine of the angle the line makes with the x-axis, while the y-coordinate of P is exactly the sine. Therefore, if we call this point here Q, then we know that the length of the segment connecting P and Q is exactly equal to the sine of alpha. If instead we draw the line which is parallel to the y-axis and goes through the point 1, 0, and we call the intersection between the line on which the radius we drew lies and this line R, then the length of the segment connecting R to 1, 0 is what we call the tangent of alpha. Using this picture here, we will prove the assertion above. How do we do this? Well, here we've got three things we can compare. The first one is the triangle whose vertices are the origin, P, and Q, and it's the one I just colored in blue. And we know that the area of this triangle is given by sine of alpha times the cosine of alpha times 1/2, because this is a right triangle. We also have another triangle, which is the one with vertices O, R, and 1, 0, and the area of this other triangle is given by tangent of alpha times 1/2, because even this triangle is a right triangle. And finally, we've got the angular sector in whose angle is alpha. And to compute the area of the angular sector, we can use the proportion alpha is to 2 pi, as the area of the angular sector is at pi. Therefore, the area of the angular sector is equal to alpha divided by 2. Now, from the picture, we can see that the triangle OPQ has definitely area smaller than the angular sector, and the angular sector has area smaller than the triangle OR10. Therefore, we get the inequalities sine of alpha times cosine of alpha times 1/2, smaller or equal than alpha divided by 2, smaller or equal than tangent of alpha times 1/2. We can multiply everything by 2 to eliminate the denominators, and then as everything is positive, we can turn these inequalities the other way around, by which I mean, as we have alpha smaller or equal than tangent of alpha, this implies that 1 over tangent of alpha is smaller or equal than 1 over alpha, and sine of alpha times cosine of alpha smaller or equal than alpha implies sine of alpha divided by alpha smaller or equal than cosine of alpha. Therefore, putting these two things together, we get that sine of alpha divided by the tangent of alpha, which we know is equal to 1 over the cosine of alpha, is smaller or equal than sine of alpha divided by alpha, which is smaller or equal than cosine of alpha. And this is true for every alpha bigger than 0. Now, if we come back to the picture here, we can see that if alpha is near 0, then cosine of alpha is near 1, because it's the x-coordinate of the point P, and actually cosine of 0 is equal to 1. Therefore, if we use this thing in inequality we've got here, then the quantity here on the left is near 1 when alpha is near 0, and the same is true for the quantity on the right, is near 1 when alpha is near 0. Therefore, as sine of alpha divided by alpha is between these two quantities, it must be true that sine of alpha divided by alpha is near 1 when alpha is near 0. In particular, if we write once more the formula we had before, which was 2 pi times the sine of pi divided by n divided pi divided by n, then when n is large, which means we are taking n very, very big, like for example n equal 10 to the 9th and so on, we get that sine of pi divided by n divided pi divided by n is very near to 1, which means that this number is very near to 2 pi, which is the correct answer for the length of the circle. Therefore, we proved that using our definition of length of a curve, we can recover the known length of a circle of radius 1. In the exercises, you will have the chance to compute the length of circles in other metrics. For this lecture, we're done, and I'll see you in the next lecture, in which we will look at metrics on the sphere. So see you in the next video.